Great. So thanks very much for this opportunity to share with the community with some of the recent results that we have obtained in the direction of aeroacoustic prediction and shape optimization using SU2. So here I will present some of the joint venture between my team at the University of Bristol and also and Professor Alberto Guadona's team at Polimi. I will have to apologize. I just noticed that one of the main contributors of this work, Luca Albergo's name is for some reason missing on the first slide, so I'm sorry about that. Okay, let me try to flip the slides. Oops. Okay, so for this talk, this is a two-part talk. In the first part, we're going to talk about some high-fidelity LES based simulations for propeller noise prediction, mostly focused on broadband noise. And in the second part, we're going to talk about more in the direction of shape optimization to reduce the tonal noise of propellers. So as you can see, both talks are focused on propellers and rotors. So you might ask why that is the case. So what's the hype? So we are in a new era of zero emission aviation, thanks to the rapid advances in electrification and automation. So and this new era is marked by the emergence of UAMs and DEP concepts, and the noise is indeed identified as one of the leading concerns of UAM and DEP by different recent studies on social acceptability. And it's been well documented that the aircraft noise has a very detrimental effect on health. And propeller noise by far is a dominant noise source in different UAM and DEP concepts. So so certainly it deserves a lot of research effort. So looking at propellers, some challenges and opportunities. So firstly, some challenges. So first of all, these propellers for UAMs, they're getting smaller, rotating at much lower tip velocity than the standard typical turboprop propellers. This means effectively that the relative importance of broadband noise contribution in relation to the tonal component is elevated. And as far as broadband is concerned, there's a few key flow features that we need to accurately capture. So for example, laminar separation bubble transition and the reattachment, and all these occur in smaller scale propellers. However, the flow physics and their related noise generating mechanisms as such low to mid transitional Reynolds number are not very well studied or understood, and partly part of this has to do with the fact that it's almost impossible to measure experimentally some of the key quantities on the blade level. So what's happening on the blade surface, for example, transition separation line, wall pressure spectra, etc. So to be able to do this, we need high fidelity flow simulation in order to really look at what's happening on the blade and what's generating the noise. This also leads to some opportunities. So for example, on the bottom right here, you see some innovative blade shape design. So we for example have looked at different blade tip design to reduce noise. And also optimal noise control, which is enabled by the enhanced propeller control authority in UAMs, meaning for these UAM configurations, we are able to to have RPM control, pitch control, and also tilt the rotors and stuff and things like that. So without further ado, I will start with the first part of the talk, which is on the high fidelity simulation of propellers. So for this study, we look at a two-bladed 9x9 propeller designed by Meslick. So the first 9 of the 9x9 means that the propeller is 9 inches in diameter. So that's about 23 centimeters in diameter. And for this very propeller, we have our in-house test data collected from our aeroacoustics wind tunnel in Bristol. We perform well-resolved LES using SU2 in order to study the detailed flow physics and noise generation mechanisms. This means that we don't do any wall modeling. We don't rely on any sort of turbulence model. We resolve all the way down to the wall to capture the flow physics. And you will see in the upcoming slides why this is very, very important. We looked at two different operating conditions. One is the first one is the static or hover condition. So at advanced ratio equals to 0, and that's what you see on the left here. Here we're plotting the Q criterion isosurface colored by the velocity magnitude. The second flow condition is the forward flight case at 15 meters per second, and for both conditions, the RPM is set at 6,000. We work with three different grids at increasing resolutions. For this talk, we'll focus on grid 1 and 2. So G2 is about 250 million cells, and so this is if you look at the X plus Y plus and Z plus, it's on the verge of so-called qualifying it to be well-resolved LES. G3 is quite a bit finer. It's about it's 500 million cells. And for all these three simulations, we run them on the UK national HPC cluster, Archer 2. And these are massively parallel simulations using about 15,000 cores for each job. Okay, so before looking at noise prediction, let's look at what's happening on the blade, what LES can get us. So if you look at the static case, so J equals to 0, you see directly that the flow separate at the leading edge, and this is somehow to be expected because these propellers, they are not optimized or designed to operate well at takeoff or at hover condition. For forward flight, which is advanced ratio of 0.66, you see that the flow is attached in the first about 40% of the chord, and then you've got a based on what you observe from the wall shear stress, you see a laminar separation bubble picked up by the simulation, which spans across a large portion of the blade, and also turbulent reattachment near the trailing edge, and this is very much consistent with the findings by our colleagues from the aeroacoustics team at TU Delft, using a pretty similar propeller using oil flow visualization and also lattice Boltzmann simulation. Okay, so it's quite informative to compare the difference between rounds and the LES simulation. So first, let's look at the pressure distribution, and you see that for rounds computed using rotating reference frame, the surface pressure actually compares quite well with the mean LES solution. So this basically means that if you use for such a case, if you use a round solution, you will get a pretty accurate tonal noise prediction. However, in the trailing edge region, what you see is that the turbulent fluctuation there is completely missing in a round simulation. And what's more informative is actually looking at the wall shear stress. What you see again is that for LES, you have a large laminar separation bubble across a portion of this big portion of the span, and you have the turbulent reattachment. On the other hand, for rounds, rounds completely mispredicts the wall shear stress, and as a result, the separation line separation occurs much too late, and there's no more reattachment. Much of it has to do with the fact that with rounds, we're not using a transition model, so it's using the fully turbulent assumption, which is for such a low to medium Reynolds number flow, it's not true anymore. Okay, now let's look at noise. So for the static case, we see that the tonal noise level at the blade passing frequency is under predicted, as you can see here, by about 3 to 5 dB. The broadband level also is between 2 to 10 kilohertz, also under predicted, and this is the cause of this misalignment is actually due to the fact that we are in LES, we're simulating rigid blades, whereas in reality, in experiment, for such a highly loaded blades, at static condition, they actually flex quite a bit. So there's a lot of aeroelastic effects that we are not capturing with LES. However, the shape of the spectrum and the decay rate are indeed very accurately captured. And there's also very little difference between the two grids, between G1 and G2 grids. Things are behaving much better. The prediction is much better in a forward flight case. So you see that the tone is very accurately predicted within a couple of dB. The broadband range up above 2 kilohertz is also very well captured. We do have some mismatch in the low to mid frequency range. This is actually due to the fact that the insulation and the scattering effects from the propeller rig is not captured by such a isolated propeller simulation. And also above 8,000 hertz in the experiment, we have some contamination from the loaded motor noise, as you can see here. G2, so the finer grid is slightly more accurate than G1, and you don't see any spurious noise between the 3 to 5 kilohertz range. So now if you look at the overall sound pressure level, we see that the deviation is from the experiment is maximum 2 dB across all the microphones. Okay, with this LES simulation, we are able to extract some very useful blade level information that are not easily experimentally measurable, and we can use this information to develop and tune engineering models for propeller noise to help the industry design quieter propellers with much lower time to solution requirement. And what the movie you see here is the pressure fluctuation at the trailing edge. You can clearly see that the broadband noise region. Whoops. Some current effort, we are currently analyzing the results from the finest grid G3. We're looking at now simulations at much higher advanced ratios. This will increase push the tip Mach number much higher, and from there we want to investigate the effect of volume noise source term. I should point out that the acoustic prediction is based on the solid surface Fox-Williams-Hawkins, which ignores the volume source term so far. To enable simulation at higher Reynolds number, we are planning to look at wall model LES. as well. And from the simulation, from the experimental side, we're trying to do some PIV wake measurement and oil flow visualization to help cross-validate with the simulation. Some ongoing effort. We are now looking at also edgewise flight, and this is where you know the flow is coming in at a large angle, and this is quite relevant for UAM type of applications. And this is just some animation of what's happening when you subject this the forward flight propeller at a large angle of attack. And you see some very interesting features, noise generating phenomenon. When you go from 0 to 15 degrees angle of attack, you see that the unsteady loading region outside of the broadband noise zone, it has enlarged. So this means that we expect a much larger tone and also broadband level. Okay. Now I come to the second part, which is the optimization part with based on runs. And this work is yes.
Note you have 3 more minutes, and we're already in the question section. So if you keep it short, that would be great.
I'm gonna try. Thanks. So this work is led by Luca Albergo from Polimi, and basically the idea is we set up the adjoint solver using based on runs and Fox-Williams-Hawkins in SU2. Here we only target the tonal noise component, and we apply this optimization framework to optimize constant pitch to diameter ratio blade with a swept tip, as you can see here. And this propeller has been tested in our own wind tunnel, and the RANS FWH prediction indeed validates against the experiment for the baseline case. We use steady runs simulation in rotating reference frame, and what we do is that the surface pressure we replicate it in the F1A solver. We make it rotate inside the F1A solver to simulate the effect of blade rotation. So we perform a joint-based optimization for these blades. 2 optimizations were performed: unconstrained noise minimization and the thrust-constrained noise minimization. As you can see, for the unconstrained, the constrained one, the shape change is a lot more minute, whereas the unconstrained one, you have very drastic shape changes. You can probably see it more clearly here, and this is, I believe, is the last slide. Yes, so for the unconstrained case, you get very drastic noise reduction, about 12 dB, but this is also corresponds to 80% loss of thrust. On the other hand, thrust-constrained noise minimization, we're able to exactly constrain the thrust with a more moderate noise reduction of about 3 dB. And I believe that's it. Thanks very much for listening, and thanks everyone who has contributed to this work.
Yeah, I think we probably have time for one quick question before we transition to the next presenter. Yeah, Harsh. Yeah, the question is whether there's a working implementation in SU2, so that, or a test case that people can pull and try on their own.
For which part? So for the first part, the LES based simulation, we use implicit LES and also explicit LES with Freeman SGS, and that's already in the develop branch. We do have a working implementation for for the F1A, so the FWH solver as well. So if anybody interested, you can reach out to me, or you can reach out to Luca Albergo, and we can help you get that set up.
Okay. Okay. Nico follows up with when FWH will be, in the main version. When will it be developed and mastered?
I would say.
Does it exist in a repo somewhere?
Yeah, or does it exist in a public repo so that it can be publicly accessed?
I don't believe so. I think this is a branch that Alberto's team and my team we're using, but we are indeed planning to merge it into the develop branch, of course.
How was it distributed to Luca?
Okay, last question. Pedro asked, how was it distributed to Luca?
How was it distributed? Sorry.
How did Luca? How did you gave access to Luca to the FWH code?
Well, there was a branch that I had a while ago, and I think Luca just pulled it, and we have now our own branch. I think the detail of where this branch is, you have to check with Luca.
Okay, thank you. I think we're out of time. Let's thank Beckett once again.
Thank you.